So for the next 40 minutes, I'm going to just sort of talk about my experiences building an application that's got, which is for me has quite a different architecture. So I'm using Scala, which is actually something I've been using for a while, but I'm using microservices along with a functional domain model, and then some really interesting architectural patterns, event sourcing, and command query responsibility separation, CQRS, and along with Spring Boot. So it's sort of a mixture of new stuff and old stuff, and it's been quite interesting. And for me, and I hope that you will find it interesting as well. So a little bit about me. So I actually started software development way back in the 80s, actually programming in, my sort of first real job was programming in Lisp, building compilers, runtimes, and IDEs and so on. Lisp, of course, being a very early functional language. By the time I started using it, it was object-oriented as well. And then, of course, eventually I started using Java. And about 8 years ago, I wrote the book Pojos in Action, which was all about building apps with Spring and Hibernate, which back then were these pretty radical technologies. Some of us still like them. And then back in 2007, I started tinkering with this obscure thing called EC2, which, much to my surprise, sort of turned into this kind of whole cloud computing industry. And along the way, I created a startup, Cloud Foundry, which then got acquired by SpringSource right before SpringSource was acquired by VMware. And I like to joke that, in fact, Cloud Foundry was sort of much more of a plankton than a fish. Otherwise, I would be fabulously wealthy and have my own island by now. But I still work, and I'm working on a startup right now, and I'm also doing consulting. So here's the agenda. So I'm going to talk about why we want to build event-driven microservices. And then I'm going to talk about how this technique known as event sourcing fits in really, really nicely and solves some of the key data consistency issues that you get in a microservice architecture. And then I'm going to talk about some other sort of different aspects. Then I'm going to finish up by talking about how you can build and deploy microservices using Spring Boot, which is sort of one of the newer technologies within inside the Spring ecosystem. So why microservices? So let's imagine that you're building a banking application. And I want to apologize to anyone who actually is working in banking, because my example is really, really naive. I'm probably wrong in a lot of different ways. But you could imagine you've got a domain model like this, where you've got an account that has a balance and operations like open, debit, and credit, and so on. And then you have transactions like a transfer transaction that transfers money from one account to another. So you could scale this up some. And if I was to implement this sort of using the way I've been doing for most of the time that I've been building enterprise applications, I'd have a UI component. I'd have various back-end modules, like one dealing with accounts, another one dealing with transactions, perhaps another one dealing with customers. And so I'd have this nice modular architecture. And I would have used Spring MVC and Spring and Hibernate as sort of the infrastructure frameworks to kind of deal with persistence and transaction management and so on. But I take my nice logical architecture, and then I just package it up into a single monolithic application that I would then run on top of Tomcat. And there were pretty good reasons for doing it that way. Apps like this were pretty simple to develop, pretty simple to test, and pretty simple to deploy. You had one file that you would just drop onto an app server, and it would just run. And if you wanted to scale it, you just ran multiple copies behind a load balancer. And for the longest time, that was the way I built applications, and probably a lot of you did as well. But as you all become, we're sort of becoming increasingly aware, monolithic applications sort of basically don't scale. They don't really deal with complexity. And there's probably some of us in the room who are now living with a million-line monolith that they're just absolutely afraid of touching, because it's intimidating. You just don't know how to make changes. It's got complex build, process, and so on. Tends to be an obstacle to frequent deployments. Ideally, we want to deploy to production many times a day, but if we've got this large monolithic application, that's really difficult. A large code base also overloads your IDE. Just slows things down, makes you less productive. It also slows down the application server as well. So if you're going through the make a change, start up the server, try it out, and your server takes minutes to start up, that's going to make you very unproductive. And it tends to be an obstacle to scaling development. You want to sort of functionally decompose your team. You know, if you've got a large engineering team, you want to have one team working on accounts, another team working on transactions. And, you know, but then if at the end of the day, they've all got to package up their code inside this single WAR file, that requires a lot of communication and coordination and so on. And then also, a monolithic application requires sort of a long-term commitment to a particular technology stack. It's very difficult to upgrade to newer technologies because you have to rewrite large amounts of code. You know, even today, I still run into people who are using EJB2 and struts, which are, you know, from the dark ages of enterprise Java development. So obviously, the solution here is to functionally decompose your application into a set of standalone services or microservices. You know, so each service has one very tightly sort of focused set of responsibilities, typically just one function. Each one has its own database and so on. And that really addresses many of the problems on the previous slide. Then another problem with the traditional architecture is that we've all sort of got very used to using a relational database. The trouble is that sooner or later, we're going to run into issues around scalability. Or maybe it's difficult, we want to have a distributed database infrastructure. Schema updates on large tables can be a problem. And of course, there's the traditional sort of object relational impedance mismatch where we've got our nice object model and we have to map it into a relational schema. And then also relational databases are not very good with handling semi-structured data. And here now, of course, the solution is to use one of these trendy NoSQL databases. So if I want to use text search, I could use Solr or Cloud Search. If I want to store social data, I could use a graph database like Neo4j. And if I wanted a highly distributed database, I could use Cassandra. So, you know, sort of the model we're moving towards is microservices plus NoSQL databases, or polyglot persistence, where we're using a mixture of different types of database. But then we actually, you know, we've solved some problems by doing that. But now we've sort of kind of entered we've encountered some other problems. Basically around data consistency, we've sort of partitioned up our data, but we still need to keep things in sync. So that's deeply problematic if we don't have two-phase commit, both with microservices and also with NoSQL databases as well, where we've sort of got lots of denormalized copies of our data that need to be synchronized. So the solution, of course, is to have an event-based architecture where services publish events when their state changes that other microservices can subscribe to, and then they can synchronize their replica of the data. So we end up with an architecture that looks like this, where you've got, you know, in the banking example, we've got transactions over here and accounts over there, and they're sort of publishing and subscribing to each other's events and keeping them both in sync. The trouble is that if you dig into it, reliably generating events is quite tricky without two-phase commit, because we need to atomically update a database and publish events as well. There's a really good article by one of the guys who worked at eBay about their approach. And it sort of just ends up being a very tricky problem once you get into it. If you want to commit your data to the database and be sure of publishing an event. And that's where this technique known as event sourcing comes in. And the big idea is that you're sort of taking a very event-centric approach to your domain model. So for each aggregate, you identify the state-changing events, and you define explicit event classes. So for an account, you'd have events like account was opened event, account debited event, account credited event. And likewise, for a shopping cart, you'd have events corresponding to items being added or removed and the order being placed. And then this is where it gets really interesting. Instead of storing the current state of an aggregate, you actually store the sequence of events that led up to its current state. So instead of having an account and storing data in an account table, you have an event table that stores the sequence of events that occurred to that account, like it was opened, it was credited, it was debited, and so on. And then to reconstitute the current state, you replay those events. So you actually load the events from the event store, replay them to reconstruct to reconstruct the current state of the account. So it's a very different style of programming. And you end up with something with a domain model that looks like this. I've got a few little bits of Scala code, because all of this is kind of written in Scala, of course. So I've got a couple of base traits that my domain classes extend. So the first one is aggregate, and that defines an apply event method that captures the process of applying an event and returning an updated aggregate. So it actually, the apply event is a function that returns a partial function from event to t. So that's, you apply an event, you get back an updated aggregate, because it's the domain objects are immutable in my model. And then the command processing aggregate extends aggregate and adds this process command method that plays the role of taking a command that represents an incoming request, and applying that to the aggregate and getting back a sequence of events. Then here's the account class, and you see the process command method makes really nice use of Scala. So it's a case class, which has some benefits that I'll talk about on the next slide. And you can see that process command rather, is doing pattern matching against the various commands that are flowing into the aggregate, and each one returns a sequence of events. Usually it's just one event, but there are scenarios where you might return multiple events. So it's sort of splitting up updating into two parts, generating the events and then applying them. And so here's the apply event. So it's a partial function that matches against events and then uses the copy method that's conveniently generated, because it's a case class, to actually return an updated copy of the account. So you can see that debit just gives you a new account where the balance has been decremented by the amount that you're debiting by, and credits are going in the other direction. So that's what your domain objects look like, which are kind of different and slightly weird. But it's all very, very event-centric. And in more elaborate aggregates, instead of just having, say, a single balance field that's a big decimal, you can imagine much more complex, much more elaborate structure. And you could also imagine using techniques like lenses to do the update and so on. But in this architecture, requests are handled sort of like this. So you've got some kind of adapter that's handling HTTP requests. So an HTTP request comes in. The events for an aggregate get loaded from the event store. A new aggregate, in this case it's an account, is just instantiated. The events are replayed to reconstitute the current state. And then a command is processed, which generates some new events, which are then persisted in the database. So that's sort of the flow. So we're no longer preserving the current state. The persistence is done in terms of these events. And in one hand, there's definite just benefits to doing that. But in the broader context of a microservice application, why this is really useful is for the simple fact that the event store will publish these events when they're persisted. So it's kind of acting as a combination of a database and a message broker, and sort of transactionally publishing these events. And then other microservices can subscribe to those events, and then they get notified when the events are getting saved, which then enables that other microservice to update other aggregates. So it means that we can change an aggregate over here in one microservice, and another microservice can then update its aggregate to keep it in sync. So we're sort of solving some critical problems there. Or it could update some other data in some NoSQL database or in a relational database that's sort of a denormalized copy of that data for some reason. So it's kind of letting us synchronize a view of data with the system of record. So we're sort of killing two birds with one stone. And the actual event store API is a bunch of sort of, looks like someone sat on the keyboard because of all the type constraints and so on. But you can see there's like a save method which saves a new aggregate in the database. So it takes the aggregate and the events, update, saves an updated aggregate, and then there's some find methods. And then down here, there's actually a subscribe method as well, which is how an event consumer can subscribe to those events that are coming out of the event store. And that's actually, right now, it's implemented using RxJava to represent the stream of events that are flowing out. Though there's sort of some work that needs to be done. And everything is asynchronous because, that's the way to build apps these days. And I actually plan to open source this at some point. And if some of you are probably wondering, well, why aren't I using Akka persistence? And there's sort of a bunch of reasons around that. But one of them is I find Akka persistence is much too sort of Akka-centric. Not everything should be or needs to be an actor, among other reasons. So there's a bunch of benefits to doing things this way. So number one, from sort of a business sort of domain modeling point of view, we get this built-in audit log. So this stream of events, which are representing the state changes to our system, just happens to be an audit log of the changes. So we know what was changed when, and if we're including user information in those events, we know who made that change as well. So we've got this nice auditable system that's quite important in a lot of domains. And then another really interesting thing is because we're no longer storing the current state, but a sequence of time-stamped events, we can reconstruct the state of the system at any point in time. So we can basically sort of do these historical or temporal queries, like what was the state of this account on this particular day, which is quite useful. And then to go back to solving some technical concerns, which was the motivation for using this approach, it solves some really key data consistency issues in a microservice/NoSQL-based architecture. So this event store is atomically saving and publishing events. Other services can subscribe to those events and update aggregates. So we get basically like this workflow mechanism. So we can debit one account over here in one sort of step, and then an event will trigger the other aggregate, the other account to get credited eventually. And then, as I mentioned earlier, it enables views stored in either SQL or NoSQL databases to be kept up to date. And it also solves the OR mapping problem, because effectively in this system, there's simply an event table. So rather than tables specific to each entity within our system, in which we then have to think, well, we've got this object model here, how do we map it to the database? And instead, it's all going through these events, which sort of inherently have a much simpler design. So that's quite nice. It's really nice not to have to deal with OR mapping anymore. Whether you're doing it with an OR mapping framework or by hand, you still have to deal with a mapping problem. The downsides, of course, is that, well, this is kind of a weird and unfamiliar way to do things, right? Our domain objects look quite different. How we're persisting things look quite different. So it's sort of a bit of getting used to. Another really interesting thing is our events really end up being like, because you're effectively storing events from the beginning of time, and they're immutable, you make mistakes at the beginning of the project, and it's kind of tricky to sort of recover from them in a way. And I've actually, in the app that I've been building, I've sort of been encountering that. It's like, oh my God, I can't believe I did that. But unlike with a sort of a system where you're storing the current state only, and you can just do a schema migration to fix things, you know, the events are frozen. So that's kind of tricky. And then, of course, in any event-based system, you end up having to sometimes deal with duplicate events, because sort of implementing a message or an event store or a message broker with exactly one semantics is really, really tricky. So it's usually at least once, which means under some circumstances you might see the same event twice. And sometimes that's not a problem because you've got idempotent commands. But other times you end up having to do duplicate detection, like keep track of the most recently seen event, and if you see one before that, then you know that you've processed it. So there's a little bit of work. But on the whole, it's sort of been an interesting and useful approach. So kind of going up a level and looking at, well, what do microservices look like when you're using this approach? You know, the sort of the design pattern I'm really following is that now a microservice really implements one aggregate. Or possibly you could bundle aggregates together and package up the code for multiple aggregates inside one service. But there's sort of this fundamental chunk of design, and then you actually have flexibility as to how you package it into services. So you have an aggregate. Then there's various adapters that are handling requests using a variety of different protocols from the outside world, HTTP, or they could be plugged into sort of more enterprise-y message buses and so on. And these adapters are turning those incoming requests into commands that get processed by the aggregate, which then saves its events in the event store. And then on the flip side, an aggregate subscribes to events being published elsewhere. And there's an event adapter that takes an event, turns it into a command, and then has it processed by the aggregate, which generates events, which get persisted. So that's kind of the model, sort of the standard design pattern that I'm following. And then, you know, so if we were to take a slice through one of these, what does it look like? So, you know, so here's an asynchronous Spring MVC controller. So that's layered on top of the async servlet API. And so it's taking an HTTP request, a post request to create a transaction. The Spring MVC is nicely turning the JSON body into a transfer details that's got the from account, the to account, and the amount to transfer. And then it's calling a transaction service over here to transfer the money. And it's all wrapped up in a for comprehension because this is all sort of reactive code. And then at the end, it's turning the future into a deferred result, which is Spring MVC's version of a future. And then here's the service. And sort of the interesting thing about this is that I've got this sort of what I think is kind of a nice little DSL that expresses the semantics of creating a command and having it processed by an aggregate. And here what it's saying is, so here's we're creating a create transfer transaction command and sending it to a new entity of type transfer transaction. And that arrow under the covers is actually sort of taking care of instantiating a brand new transfer transaction, processing the command, applying the generated events, and then persisting the events in the event store. But all of that's sort of hidden from you with just this sort of mini little DSL. And the transfer transaction aggregate looks kind of like the account, and it's got a process command method and an apply command method, and it publishes various events like I've been created. I've recorded the fact that the debit of the from account has occurred. I've recorded the fact that the credit of the to account has occurred. So it's generating these events. And then at the same time, it's subscribing to events that are being published by the accounts. So these, if you remember the picture at the beginning, the transfer transaction is publishing events that cause the account to be debited or credited, and that debit or credit publishes events that the transfer transaction listens to so that it can update the state of the transfer. So in this particular case, it's using another sort of version of the DSL to say, for this particular event, for this debit event, go find the existing transfer transaction with the ID that's stored in the event, and then go tell it to process the command to record the fact that the debit occurred. And under the covers, it's doing the load from the event store, processing the command, applying the events, and then persisting the events again. So that's kind of like what all these sort of the adapters, both at the HTTP level and at the event handling level, look like. And so it's kind of an interesting style of design. But there's one interesting thing about this is that the event store, as a database, has a very primitive API. It's basically load by primary key. Yet, if you look at a screen on a typical application, you're getting data from multiple aggregates, possibly, and you're doing joins and quite, relatively complex things. So let's imagine, in this banking example, when you log on to bofa.com or Wells Fargo, you look at your account and it's displaying a whole list of, you see the balance and a whole list of recent transactions. And with the design that I've been talking about to do that, you actually need to do a join between the accounts and all of the transfer transactions that have impacted that account, either transferred money in or transferred money out. So it's sort of, if we were doing this in SQL, we'd do some kind of in or out of join between those two tables. But you can't do that with an event store because it's primary key based. And so that's where this other architectural pattern, command query responsibility separation, comes in. And when you apply that, you define separate views or separate database tables that store in a denormalized form the data that's needed to support the query side of your application. So the event store is supporting the command processing side of the application. It's publishing events that these views are now consuming so that they can build up these sort of materialized or denormalized views of the application's data. So basically, for to support the queries, you define some number of views, and those views use the database technology that's best suited to the queries that you need to execute. So, if it could be Cloud Search or Solr or Elasticsearch for text search, Neo4j if you need to kind of do searches of social graphs, or MongoDB. It's really, really useful because you can have quite large JSON documents stored in Mongo that you can just access with with a query or even a primary key lookup, and you just get a blob of JSON that you can then hand back to the browser, which can then render all of this data. So you have these views. And then in terms of microservices, you have an updater that subscribes to the events coming out of the event store and updates the view. And then there's a query service that responds to HTTP GET requests and queries the data. And then in one of the example apps that I built, I represent accounts as an account and its recent transactions as a single document inside in MongoDB. So, we've got the account, got the balance, then you got the transactions that have impacted that account in some way, caused debits or credits to occur. And then I actually store the list of the recent debits and credits. So it's a very sort of denormalized representation. But with one primary key lookup, you can grab that MongoDB document and pass it back to the browser, which can then render it. So that's kind of a really nice pattern. And got a bit of code here, but so you've got an events handler that's subscribing to various events, and then just doing in-place updates of a MongoDB document. So key thing is it's doing just pushing changes onto that list of changes inside the document. So we don't even need to read it from the database, can just do an in-place update. And that's all done quite nicely with Spring Data for Mongo. yet another Spring project. And the queries are also quite nice as well. You don't even actually have to write any query code. Those get auto-generated by the Spring Data for Mongo dynamic repository mechanism. So that's sort of the view side of the app. So we've got the event store that's sort of acting as the system of record, and then we're storing denormalized copies of that data inside Mongo to support sort of the UI. So final part of the talk is just about how you've got these apps, or you've got all this code, how do you build and build it, turn it into an executable application, and then actually deploy it into production. So the technology that I've sort of been using recently, and I've sort of been very excited about, is Spring Boot, which is yet another project inside the Spring ecosystem. And you can think of it as a framework and tooling that sits on top of a whole bunch of other Spring projects that makes it super easy to package up your application as an executable jar file. So it's ready to run. And it uses convention over configuration to configure your app. So you have to write very little configuration yourself. It also makes it easy to externalize configuration, like the host and the port and the user ID and passwords of any databases or other infrastructure services that you need to talk to. And you can actually supply at launch time a separate config file, or it can grab it from environment variables or from the command line, which is really, really nice. So you really do not have to write any code to do that. And then there are plugins for the IDE for various, for like, Gradle and Maven that spit out executable jar files. So, probably some of you have used Spring, and you know that when you're using Spring, you write your application components, but then you have to supply configuration metadata that tells Spring how to assemble and configure your application components. So way far, a long time ago in the distant past, you actually had to write XML. But since about 2007, you haven't had to do that. So in the beginning, around about then, annotation-based configuration was introduced. And then more recently, there's Java configuration, where you're writing Java code to do the configuration that uses some annotations as well. And that gives you some nice type-safe configuration that's statically typed, which is really quite good. And the neat thing is that, and so it actually got to the point where in the beginning, you had to write tons and tons and tons of XML. And then with those two things, you ended up having to write very little config code. And now with Spring Boot, you end up writing even less. Because it does things like look at the jar files on your class path and say, well, you've included a database driver. Therefore, you must be accessing a relational database, and so I automatically define all of the components, like the JDBC transaction manager and the JDBC data source, so you don't have to write those yourself. And you end up writing very little config. So this is basically the configuration for the Java service. So it's a configuration class, and there's sort of an configuration annotation on it, and that's basically it. And then you also have to write a main program. And all that's doing is calling Spring application.run, passing in that configuration class, and then also any of the command line arguments, and you're good to go. And then building your app is quite straightforward. So because there's plugins for Gradle and Maven, so you just, Gradle build will give you an executable jar file that's got command line arg processing that's really quite nice, so you can tweak the port that the server listens to. And it also gets health checks built in as well. So if you ask the application on the /health URL, it actually tells you about the status of the things that your application is talking to, and that's an extensible mechanism. And so you get all this stuff for free, which is really, really handy. So I'm making use of that. So each microservice is now a Spring Boot application. And then the other part of it that I just sort of throw in there because Docker is cool. So I have a Jenkins-based deployment pipeline that's building and testing the application. And then it's taking the executable jar file, packaging that up inside a Docker image, and doing a smoke test of that. So it launches the container and then pings the health URL to make sure that it's kind of functioning. And then it uploads it to a Docker repository, and from there it gets pushed into production. And it's one of these build pipelines per microservice. So anyway, so that's sort of kind of a whirlwind tour of sort of this sort of the way I've been building apps recently, and I hope that you found it useful. So the key thing is that event sourcing solves some really critical data consistency problems that you have when you're using microservices, and also that you have when you're using either NoSQL databases or multiple relational databases. And then I also think, Spring and Scala play nicely together. I've been building apps with Spring and Scala for a number of years now. And then Spring Boot kind of makes it really, really easy to take those apps and package them up as sort of executable, ready to go, production-ready applications. So anyway, that's my talk. Hopefully you can follow me on Twitter, shoot me an email, and you can find more information, slides, and whatever on my blog, plainoldobjects.com. So thank you. And there may or may not be time for questions.
We have time for questions.
Yeah.
So how do you deal with large construction works? For example, in this model, there is also a
Actually, could you speak up just a little?
How do you deal with large transaction logs?
So the question is, how do I deal with large transaction logs? I'm not sure. I don't. So the event store is currently sitting on top of other. Actually, right now it's sitting on top of DynamoDB, though it could sit on top of other databases as well. So there's that. But I mean, is your question referring to the fact that every time there's a new transaction, I'm pushing onto the list? Well, the thing to do is you could have a separate task that then trims that list, right? Like drops old entries off the back. Like, just preserves the last, like if you go to your, the last n days of transactions. You can do it that way. Yeah, you're closer so I can hear you.
Okay, would you suggest actually in that same case a strategy, say collapsing records into snapshots?
Oh, okay. Yeah. So the question is, snapshots are really interesting. So yeah. So if you have some long-lived entity, then that's being updated regularly. Then obviously there's you could end up with a lot of events that when you load them from the event store, have to get replayed, and that could get expensive. So yeah, in event sourcing, there's the approach of periodically taking a snapshot, which means that you then only need to load the snapshot and then the events that occurred after that snapshot. It's like the memo pattern, right? Where you just say, ask the entity, can you just sort of give me a serializable representation of yourself? I'll save you in the event as a snapshot event, and then just grab that and any events that happen afterwards to reconstitute the current state. Yeah.
Yeah, one of the weaknesses we highlighted about saving the events and not the state, do you find that it's a problem if you want to change the behavior that's attached to those states, but you find you can't because your state will drift over time in a problematic way as you evolve, or do you find you add new events, new event types that are modifications of existing ones, and you're finding your concept of what those events should do over time?
Yeah, so sort of a combination of things. So, I mean, part of it, actually designing events is a little tricky. But so the simplest form of events really are just it's almost like you're capturing the data that came in as part of the request, and you're effectively replaying that. And yes, that might evolve over time. So you have sort of version 1 events, then you might have version 2 events, and you actually have to support both of them. So that can be kind of an inconvenience. And in general, not only, sometimes you actually have to, there's like, if you go read a domain-driven design book, there's the notion of like having rich events that have extra data in them. So the aggregate doesn't need that data to actually update itself, but then you include extra data in the event so that consumers have that data readily accessible, so they don't need to go and get it from elsewhere. And actually making the choices around what data goes in events can be tricky at times. Yeah.
So it sounded like you were using event sourcing to, in part, solve the problem of having to persist something and then notify about it, because one could work and the other could fail. But doesn't your event store itself have that problem if it's going to receive the data and then notify about it?
Yeah, that's a really interesting point. I mean, if you think about what kind of atomically committing means, right, is that you know, at some level you have to like perform an operation that truly is atomic, right? And since the event store is simultaneously persisting and publishing, kind of like you can imagine it having a transaction log that's where you insert those events, and the act of doing that simultaneously persists those events and then makes them available for publishing. So you've got that atomic step, whereas if it was a database and a message broker, then you'd have to use two-phase commit to do that atomically, or one of the things the eBay guys do is they actually use the relational database that you're storing state in as also a message queue, and so you could have basically a local transaction that committed and kind of sort of published at the same time. The downside, what I didn't like about that is that it required a lot of extra code that you'd explicitly have to write, whereas sort of this event-sourced approach just kind of is a nice uniform mechanism that just takes care of everything in one go and without any special casing at any point. Yeah?
I think my question you may have just answered, but in banking or trading, strict ordering matters a lot, and how do you enforce time and ordering in a distributed system like that?
Yes, that's interesting. So right now, sort of the event store is just a single server. And so ordering at that point is easy. But then across a distributed system, I mean, ordering is slightly fuzzy anyway, right? But the notion there are these. I mean, one of the things I'm doing is event IDs that are a combination of like system time in milliseconds plus a node ID for uniqueness. And so that's giving you sort of a rough ordering. And the event IDs are roughly monotonically increasing, though because of delays from one, they might get slightly out of order because of network delays. So there's sort of some interesting issues around that. Yeah?
I generalize the last question a little bit. You've got this event store that's avoiding ACID because you just got this long list of commands recorded. Then you're doing all your queries off a materialized view. Who's dealing with ACID on keeping that materialized view up to date?
Well, I mean, this system is eventually consistent, right? What's that? Well, that's why I began this talk with an apology. But the interesting thing, if you think about, I mean, once again, if you work for in a bank, please do not listen to anything I'm about to say. But if you work for a bank, if you look at how banks work, there is some kind of weird, eventually consistent notion, right? Like, so if you transfer money from your account to someone else's, the bank will immediately take it out of your account, right? And then eventually it ends up in someone else's account. And I'm sure that under the covers, you know, they're actually putting it in their account or whatever. But there is this sort of, you know, it strikes me that it's not as acid as you might think it, as it should be. And then, I mean, also at one time I had a brokerage account at like UBS, and if I logged on to this account after about 9 o'clock Pacific, the numbers in that account did not make any sense, right? I mean, they were doing some updates and running batch jobs, and things were seriously out of whack, like massive negative balances and stuff like that. So yeah, I don't know, maybe if you need sort of global consistency, this is perhaps not the right approach. But then once again, I'd go back to the original eBay article on this in the CACMQ magazine. You know, they were dealing with money, right? You know, it's a commerce platform. And yet they were using an eventually consistent strategy, because it's almost like it did absolute consistency was, you know, very difficult to achieve inside a distributed system. Anyway, thank you.